In this presentation, we'll continue our discussion of the properties of light. First, let's talk about reflection. We can say that light is reflected when it returns into the medium from which it came. So think of light coming through the air and hitting a metal surface, and it hits this metal surface and returns back to the air. It's reflected. And the way this happens is the light strikes material, illuminates that material. Electrons in the atoms of the material start to move more energetically in response to that energy from the illuminating light, and then these energized electrons re-emit the light by which we see the material. Some terms we have to be familiar with when we talk about reflection include the angle of incidence, and this is the angle made by the incoming ray and what we call the perpendicular, which is this straight line we see that's kind of perpendicular to the surface of our mirror, of our reflecting surface. Also, we talk about the angle of reflection, which is the angle made when that light ray reflects off of that surface, and the difference between its direction of travel and that perpendicular line again. And this perpendicular line that we have that meets our reflecting surface here is sometimes called the normal, and it's an imaginary line that again is perpendicular to that plane. And this imaginary perpendicular line is how we calculate our angle of incidence and our angle of reflection. And so if we could look at this normal and our angle of incidence and our angle of reflection and the rays, it's all in one plane, a two-dimensional plane, just like we see right here in the picture. When white light strikes out an object that we perceive as white, what is happening here is that the electrons in the material are responding to the light and re-emitting all visible frequencies. And if you remember back to last week when we talked about additive color mixing, when we have all frequencies of light, visible light, striking our eye at the same time, we perceive that as white. If the same white light that contains all the frequencies of light strikes a dark object or an object we perceive as black, then some or all of the visible frequencies are absorbed. And depending on which ones are absorbed and which ones aren't, is the color we see that object. And again, going back to last week, we talked about our red ball. And we perceive the ball as red because as the light strikes the object, it absorbs all the frequencies of visible light except for the red. It reflects the red back to us, and we perceive the ball as red. And of course, if all frequencies of visible light are absorbed by the object, this is an object we perceive as black, like ink on a page. Pierre de Fermat, back in the 1600s, came up with a principle called the principle of least time. And the principle of least time basically states that light, when it's going from one place to another, is going to take the least time. It's going to take the quickest path. And the quickest path is not always a straight line. A lot of times it is, but it's not always. So let's look at a diagram here to talk about the principle of least time. And let's say we want to get from point A over here on the left to point B over here. And of course, in this instance, the quickest is going to be a straight line. That's going to be the quickest way to get from point A to point B. But let's say here's our point A, and now here's the surface of a mirror down here. What is the quickest way for a ray of light to get from point A, reflect off the mirror, and get up to point B? Well, of course, this is not going to be a straight line because it has to bounce off the mirror. One way we can calculate this is let's look at, here's our point A, here's our point B, and let's put a point opposite of B going like through the mirror, and we'll call that point B2. This point is the same distance below the mirror as point B is above the mirror. So the shortest point between A and our imaginary point B2 is again a straight line from A to B. But again, we don't want to get to B2, we want to get to our first point B. So where this straight line between A and our imaginary point B2 intersects our reflecting surface of our mirror, then that's going to be the angle of incidence, and then the angle of reflection will take us back to point B. And that point of reflection is the point of reflection that's going to be the least time for light to travel from point A off the mirror and then to point B. Which brings us to the law of reflection. And I mentioned that briefly on the previous slide, that the angle a light ray comes in and hits a reflecting surface as it bounces off is going to be the same angle. And that's the law of reflection. The angle of reflection is going to equal the angle of incidence. So here we have this light ray coming in at about a 45-degree angle. It strikes a mirror, it's going to reflect off at a 45-degree angle. Let's say we have light rays coming here almost perpendicular at a 90-degree angle. Well, they're going to bounce right back at a 90-degree angle too. The angle of reflection always has to equal our angle of incidence. And when we talk about reflections, there's a couple of different reflections we can talk about. So far, we've been talking about light reflecting off a smooth surface such as a mirror. We call this a specular reflection because we can see ourselves in it, or it's also sometimes called a simple reflection. So simple and specular reflection are talking about the same thing. When we have a specular reflection, what we're seeing in the mirror is what we call a virtual image. And this image is the same size as the object that's reflected in the mirror. And as we look at the object, it looks like it's behind the mirror and it's at a position where if we draw lines extending these reflected rays, where they would meet, where they would converge. So the object that we see in a mirror appears to be as far behind the mirror as the original object is in front of the mirror. So as we see this lady brushing her hair in the mirror, she's probably about 2 feet away from the mirror, so she appears to be 2 feet. Her reflection appears to be 2 feet behind the mirror. And if she started stepping back, we would see her reflection moving further away from the surface of the mirror as well. But sometimes we have mirrors of different shapes. Previously, we've just talked about a nice flat mirror. But let's say we have a convex mirror, and this is a mirror that's bulging out towards us. When we have a convex mirror, the virtual image is actually smaller and looks closer to the mirror than the object that's casting the reflection. As we can see here on the left, we have this gentleman, he's looking into a convex mirror, and the reflection he sees is smaller than his actual head and also appears to be closer to the mirror. But now if he moves to a concave mirror where the mirror is bent away from him, now his virtual image looks larger than he actually is and further away from the mirror than he is. So this is when we've talked so far about specular or simple reflection when light strikes a smooth surface. But what happens when light strikes a rougher regular surface? Well, think about when light hits, say, like a page of a book, or light hits wood or something like that. Can we see a reflection in the pages of a book or in a piece of wood? Well, no, we don't. And we can't see a reflection in there because it's not a specular or simple reflection, it's a diffuse reflection. So these objects do not appear shiny and we can't see a reflection in them. And what's happening here is the light rays are still obeying the law of reflection. Their angle of incidence is going to equal their angle of reflection. But look at the surface, how bumpy it is. So some light rays are hitting on a surface that's kind of angled like this. Some light rays are hitting a surface that's angled down like this, and some in between. So all different, the surface is not flat like our mirror, it's all different kinds of angles. So the light rays are going to hit at a different angle and they're going to be bounced off at a different angle. And so we have this kind of diffuse reflection. The light rays just kind of scatter off of that rough surface. Let's move on now from reflection to refraction. And refraction is when we have light bending as it passes a barrier between one medium and another. And now, when we talked about reflection, the light rays stayed in the same medium. When light hits a mirror and bounces back to our eye, the light is traveling only in the air, it's not traveling in any other media. But when we have refraction, like in this picture here, we can see the light rays coming from the air and entering the water, and they're going to actually bend. And this goes back to our principle of least time. Our light is refracting to minimize the time taken for the light to travel from one point to another. So if the light is traveling through the same medium, air or water, it travels straight. But if the light has to go through different media, such as air or water or jelly or anything that's transparent that light can go through, the speed is going to be different for each media. So here, let's look at our picture again. So the light rays are passing from the air, entering the water, and the light does not move as fast as it does in air, so it's going to slow it down. And this causes the light to bend towards the normal, towards that perpendicular. So as we see here in this picture, the light's coming in kind of at a shallower angle, but as it hits the water, it bends towards the normal and makes a steeper angle. And now, if we had light going the other way from water into air, so it's going from the water to the air, a medium that allows it to move faster, then it's going to bend the other way, away from normal. And we can see why this happens. Let's look at this example of a lifeguard, and he sees this person in distress out in the water. So, of course, the lifeguard wants to get to the swimming person as fast as possible, right? So, which path would be the quickest to the drowning person? Well, if the lifeguard can run much faster on the sand than he can swim, and if he just tries to go a straight line, well, he's going to spend more time in the water, and that's going to take more time. But now, if he thinks about that, hey, I can run a lot faster than I can swim, he's going to spend more time on the sand running fast, and then he'll swim the shortest distance. So he's basically refracting his path to get to point B as quick as possible. And this is what light does. Light doesn't care about the shortest path. Light cares about what is the quickest path. And the same thing here with our lifeguard. To save the person swimming, he wouldn't want to worry about the shortest path. He's going to worry about what is the quickest path. And let's look at this in light rays coming from air through a glass window and then back to air again. So if the light wanted to get from point A to point B, well, we could just draw a straight line, and in this case, the shortest distance and the least time correspond. But what about if the light wants to get from point A to point C? That's a little different. So remember, the light is going to travel slower in glass than in air. So it's going to refract so that it spends the least amount of time in the glass, just like the lifeguard wanted to spend more time on the sand and the least amount of time in the water. So as the light ray is going towards point C, it refracts towards the normal in the glass as it's moving slower. And then as it exits the glass, it refracts away from normal and goes back to point C. So the green dotted line is the shortest distance from A to C, but the blue line, this refracting, is the quickest distance from A to C. So I spoke on some of the previous slides about how the speed of light differs in different media. And when we talk about how the speed of light differs, We can call this the index of refraction. And the index of refraction can be noted with that little italic n. And this index of refraction tells us how much the speed of light differs in a particular medium from its speed of light in a vacuum. And it also tells us how far the rays are going to bend as light enters this media. And we write the index of refraction as a ratio of the speed of light in a vacuum to the speed of light in our particular material. So in equation form, our index of refraction n equals the speed of light in a vacuum divided by the speed of light in the material. And if we have a medium with a high refractive index, that means that it's got a high bending effect, and the light is going to slow down the most in that particular material. So the higher the index, the slower light moves through that particular media. So what causes refraction? Well, let's look at these light waves, and we can see that as they strike the media at an angle, the part of the wavefront that strikes the medium first is slowed first, and this causes the light to bend. So in this picture right here, the part of the light that's over here hits the water first, slowed down first. This is still moving a little faster. So as it enters the water, we see it kind of tilted towards the perpendicular. So, and again, this tells us why we don't get refraction in light that hits along the line of normal or perpendicular to our boundary between our two layers. Because light hitting it perpendicular, the entire wavefront is hitting the boundary at the same time, so it's going to be slowed down all at the same time and the light won't bend. Refraction is responsible for a couple of illusions that we see quite often in everyday life. For instance, if you've ever kind of looked at something that's in the water and maybe reached out to grab it, you might have noticed it wasn't really where you thought it was as you're looking into the water. And this is because as the light rays are refracted going into the water, it kind of makes the object look closer to the surface than it actually is. And some people who do, for instance, gig fishing with spears have to account for this or they're going to miss their fish. It also causes atmospheric refraction is what causes mirages. For instance, in this where we're looking at the tree, if the air was all one temperature, the light waves would come straight to our eyes from the tree. But in this case, there's warmer air closer to the ground, so the light rays travel faster, and so we see the tree in a different place than we really expected it to be. Using reflection, we can get a phenomenon called total internal reflection. And this is when we have light traveling within a medium, and there's a boundary between this medium and another medium, and the light strikes that boundary at an angle that's either is or is greater than what we call the critical angle. And this critical angle is the minimum angle at which a beam of light will no longer emerge from the medium it's traveling in. And this varies for different media. We can actually experiment and see this if you have a waterproof flashlight and you fill up your bathtub. As you hold the flashlight under the surface of the water, and if you aim it kind of straight up, the light comes up out of the water and you can see the light. And then as you gently rotate the flashlight, getting it more and more towards horizontal, you'll start to see that the light is coming out and it's refracting, so the light is bending. And right about when you get to this angle, okay, the light hits the boundary between the water and the air, and it's bounced back. It doesn't leave. So even though the flashlight's still pointing up towards the air, it's being all reflected back into the water, and you won't see the beam of light come out of the tub anymore. We can use internal reflection in things like glass prisms, and they're used in many optical instruments such as binoculars. And binoculars magnify an image for us using two lenses, the ocular lens and the objective lens down here. But to make it useful enough to magnification that's useful enough for us. If we just had the two lenses, the ocular here by our eyeballs, and the objective here pointing towards our what we're looking at, it would have to be real long. Think about in pirate movies when they're trying to see a ship on the horizon, they have that big long spyglass. But with binoculars and using internal reflection with these prisms, we can still get that long path between the lenses, but now it's going through these prisms. So now we don't have to have a long barrel in our binoculars. They can be quite short, and we can get the same magnification that the pirate did with his long spyglass. And the reason we have to have two prisms is as it comes out of the one, it inverts it, and then this re-inverts it so it's right up. Total internal reflection is also used in things like what we call optical fibers, or sometimes they're called light pipes. And these are very long, thin, flexible rods or threads of a special glass, or sometimes it's plastic. And this glass or plastic has a coating that does not allow the light to come out. And as we shine a light on one end of the rod of glass, it's internally reflected off of that coating all the way to the other end. So it transmits the light from our source all the way down to the other end of the pipe where we're using it. And properly constructed, we won't lose any of the brightness of the light. And in addition to light, we can also send data down through these light pipes. So if you have something like, say, Fios at your house, this is how the TV shows and the internet gets to your house. So here we can see a diagram of the light coming in the optical fiber, and it's reflecting back in. So all the light is transmitted to the end of the fiber. And this is often used in instrument displays, like in cars and airplanes. We can use it in, for instance, in dental procedures so the dentist can see into your light easier. It's also used, say, in surgery or other medical applications to look inside the human body in various regions of the body where we really can't see. And again, like I said, with the also used in communications. So we talked about how light travels at a different speed through the different media, but different frequencies of light also travel at different speeds through the same medium. As light travels through a medium, high frequency light travels more slowly than low frequency light. And so when these frequencies are traveling at different speeds, as they go through a media, they're going to refract or bend by differing amounts. And we call this phenomena dispersion. The most familiar um, example of dispersion is using a prism. And if you have a glass prism and you shine a white light through it, white light contains all the frequencies of visible light. And as it comes through the prism, we see that it starts to bend. So first, the red light is slowed down the least, so it doesn't bend very much. Next, the orange light is slowed down a little bit more, so it bends a little bit more. Yellow a little bit more, all the way down to violet, which is the highest frequency light and is slowed down the most, so it's refracted the most. And because these different frequencies are refracted differently, they're separated out by the prism, and we have a nice kind of rainbow projected on the screen as we shine the light through the prism. This also happens in water droplets in the atmosphere, and this is what creates the rainbows that we see. As the sunlight hits all these millions and millions of little drops of water that are suspended in the atmosphere, each ray of sunlight is refracted or dispersed differently because of the different frequencies and broken into different colors. So, and when we have millions and millions of drops of water, we see this as a rainbow. Now let's move on to some of the ways we can use refraction and some of these other concepts. And one way we can use this is by using lenses. And lenses are just a device that we can use to refract light for various purposes. And when we're talking about lenses, there's a few key features we should know about. Uh, One is the principal axis, and this joins the center of curvature. So if we have a lens curving out, right where it's fattest on both sides of the lens, if we drew a line between those two fattest points, that would be the principal axis. Or if we have a concave lens where the sides come in towards each other, if we drew a line from the 2 points where the lens is skinniest, that would be the principal axis of that lens. The focal point is the point at which, when we shine a light through that lens, all the light rays come together. And then the focal length is the distance between the center of the lens and its focal point. And here we can see this in an image which might be a little bit easier to understand. So here we have the long horizontal line is the principal axis, and you can see it joins the two fattest parts of this convex lens. If we shone a light through this lens coming this way, the light rays would congregate or converge at that point right there. So that's the focal point. Same thing if we shone a light from this side coming through the lens, this focal point would be with the light rays would converge. So that's the two focal points. And then the distance between the center of the lens and that focal point is the focal lens. There's two common types of lenses. The convex lens, which is thicker at the center than on its edges, and this converges light. So when light comes through it, it has a tendency to refract towards the center. And then we have a concave lens, which is thinner at the center than at the edges, and it has a tendency to diverge light. So light kind of spreads apart as it goes through the lens. Here we can see our two types of lenses, the convex on the left, and you can see as the light rays come through, they are refracted and start to come to a point. And on the other side, we have our concave lens, whereas the light waves come through, they're refracted the other way, and they kind of spread out as they come through the lens. So we've talked about how light can be refracted or reflected, but most of the time light travels in straight lines. And you might have, maybe back in elementary school or middle school, made a pinhole camera that depended on light traveling in straight lines. For instance, might have some film back here in our pinhole camera, and then here's our object we're going to photograph. And as we uncover the pinhole, light from our object travels straight back to the film and creates an image of our object. If we put a lens in our camera, then we can create different kinds of images. And the first one we're going to talk about is a virtual image. And this is where we look at an object that's within the focal point of the lens. And remember, the focal point is where light that comes through the lens converges. So our focal point for this lens would be right there. So if we look at this flower that's in between the lens and its focal point, what we see through the lens is a right side up magnified image. So for instance, if you had a magnifying glass and you're looking at things, it creates a right side up magnified image of whatever you're looking at. But now let's move the object outside the focal point of our lens. Now it's out further away than where the light rays would converge at the focal point. In this case, we're going to get an image more like our pinhole camera. Here's our object here, and then we'll get what's called a real image on the wall. And it's the same size as our object, but it's upside down. And no lens can create a perfect image. All lenses have distortions and create distortions in images that are called aberrations. And so in most optical instruments, we use compound lenses, and which means basically we're combining lenses to correct the aberration in one lens. So the lenses kind of counterbalance each other. We can have a spherical aberration, which is where light passes through the edges of a lens and then focuses at a slightly different place than our focal point, or where light would come through the center of the lens. So you can see some are converging here, and some are converging here, and some are converging here. We can also have a chromatic aberration. And again, this is due to our various frequencies or colors of light having different speeds. So they're going to refract differently as they come through the lens. So, for instance, our blue ones are going to bend more than our red ones here. But let's change gears a little bit. Now let's start talking about light as a wave. So imagine you threw a rock into a quiet pool of water and you see waves spread out along the surface of the water from where you threw in the stone. The same thing happens when, say, you turn on a light bulb or light a match. The light waves move out from the match or the light bulb in all directions. In 1678, a scientist called Christian Huygens made a proposition that the wave fronts of light waves spreading out from a point source can be regarded as basically the overlapping crests of tiny secondary waves. So his thought was that these wave fronts are made up of tinier wave fronts. And we can state his principle as every point of a wavefront may be considered the source of secondary wavelets that spread out in all directions with a speed equal to the speed of the propagation of the waves. So every single point on this wave is the source of new little wavelets. So as these waves spread out from their source, the segments become less and less curved. So as we say, if we turn a light bulb on here, very close to the light bulb, it's still kind of a curved wavefront. Okay. But at a great distance from the source, say from the sun to here, the spherical wavefront is so big that it approaches a flat plane because the curvature is so, the sphere itself is so huge. At any point, you look at it and it looks like a plane. We can create these plane waves either by having a light source very, very, very far away from us, but we can also make plane waves in water. For instance, in this picture, this girl has a yardstick and she's dipping it into the water repeatedly, and that makes plane waves. And think of Huygens' principle. What do you think will happen as the wave hits the narrow opening? And remember, the principle states that each point on a wave can be the source of secondary wavelets. And what happens is as the plane waves go through the opening, they are bent. And this is called diffraction. And diffraction is when a wave bends but is not reflected or refracted. It's different from both reflection and refraction. Because here we can see the light's not being reflected back, the wave is not being reflected back, it's coming through the opening, and it's not being refracted because it's in the same medium. So this is a different phenomenon we're seeing. This is diffraction. And you can notice that as the light that we narrow the opening, the waves are diffracted even more. So these guys are bent the least, these guys are bent a little bit more. And then when we have this tiny opening, the waves are bent the most. So this diffraction again is any bending of waves that's not reflection and not refraction. And it's a property of all kinds of waves. And for instance, in this picture of a razor blade with a strong light behind it, we can see this diffraction around the edges of the shadows. And that's this kind of like outliney type effect you see in some of the openings here. The amount of diffraction is going to depend on the wavelength of the wave compared to the size of whatever obstruction is casting that shadow. And longer waves at a lower frequency, so our red light, are going to diffract more and fill in the shadow area and reduce blind spots. Our shorter waves, higher frequency, don't diffract as much and they cast what we call a sharper shadow and often create blind spots. We can see how this works here looking at these waves hitting these particular obstructions. So here we have some low frequency waves and hitting a fairly large obstruction. But you can see as they hit the obstruction, it diffracts quite a bit. And by the time the an observer is here, the waves would be back in sync again. We wouldn't even know there had been an obstruction there. So we call that creating a blind spot. Here we have those low frequency waves again hitting a round object, and again they're diffracted around it. But again, if we were observing down here somewhere, the waves would be coming just as regular as they were before, and we would have no idea there was an obstruction there. But now if we have a high frequency wave, we can see as they hit the object, they don't diffract very much. So if we're sitting here, we can tell there's a place where there's no waves. So there's no blind spot there. We know there's an object there. Diffraction works for sound waves as well as light waves, and other electromagnetic waves. So thinking about what we just saw in the previous slide, would a dolphin or bat be able to see its environment better with high frequency sound waves or low frequency? And of course, as we saw in the slide before, they want to use high frequency, which they do. The shorter wavelengths give more detail. There's less blind spots, less filling in of the shadows. So the dolphin can spot the fish or the bat can spot the bug easier with its using the high frequency waves. So when we talk about diffraction, and say we're shining lights through an opening, and like we saw in the picture of the razor blade, we saw some diffraction in the openings of the razor blade. If the opening is large compared to the wavelength of light, then the shadow is relatively sharp. So we can see over here, if we have a light source and a pretty large opening in our object here, we get a fairly sharp shadow. If the opening is very narrow compared to the wavelength of light, then the diffraction is going to be greater and the shadow is going to be fuzzier. So we have our same light source, but now we have a narrower opening, and you can see there's a lot more diffraction in the edges of our shadow. And this diffraction limits how small an object we can see with a regular optical microscope. If an object is approaching the size of the wavelength of light, diffraction blurs the image. And if the object is smaller than the wavelength of light, then again, we can't see it. All we can see is a blur. So things like viruses, you can't see with a regular optical microscope. So how can we see these extremely small objects? And we can use things like electron microscopes, because instead of using light, they use electron beams and electric and magnetic fields to focus and magnify the image. So we can see with these types of microscopes objects that are actually smaller than the wavelength of light. So for instance, here we can see actually these virus particles here that we could not see with a regular light microscope. In 1801, a scientist named Thomas Young conducted an experiment on interference and what we call the superposition of waves. And he noticed that if he directed some light through two pinholes and projected it on a screen, he saw these areas of alternating light and dark bands. And we know from when we talked about waves before that we can either have reinforcement of waves when they interfere with each other, or they can cancel each other out, right? So the interference pattern that Thomas Young saw was caused by these interference between pairs of waves, where they matched up with each other, they had constructive interference and caused a bright area on the screen. Where they were out of phase with each other, they created destructive interference, and so we saw a dark area on the screen. And this is what his experiment looked like. So we can have a light, shine it through a barrier that has two small openings or slits in it, and we'll see this interference pattern. And what's happening is the light is coming through the slits, and then as the waves interfere with each other, so constructive interference will have a bright area, destructive will have a dark, bright, dark, and bright, dark. And again, the constructive interference produces the bright regions where the waves are arriving in phase and reinforcing each other. And the destructive interference produces the dark regions where the waves are out of phase and they're canceling each other out. This interference can also work with colors. So you might have seen a lot of rainbow of colors on, say, a soap bubble, or maybe some gasoline or oil spilled on a wet street. And this rainbow or spectrum of colors you're seeing is produced by interference. And we often call this iridescence. And iridescence is observed in thin transparent films. So let's say we have a transparent film like a soap bubble, and this transparent film has to be about the thickness of visible light waves. And the light is going to be reflected from the outer surface of the film and the inner surface of the film. And depending on which surface it's reflected from, it's going to travel different distances. And the film in different places is the correct thickness to cause destructive interference of a certain wavelength or color. As a color is subtracted, we see its complement, its opposite, on the color wheel. So if red is subtracted, what color would we see? So here's red over here. We would see cyan over here. If we subtracted blue, we would see yellow. And if we subtracted green, we would see magenta. So as we're looking at our soap bubble or maybe our gasoline film on the street, if the angle we're looking at the film changes, say we move our head or the object moves, what would you expect to happen to the interference? Well, as either our angle of observation changes or the object moves and the angles change, the wavelength that's interfered with is going to change. So the color we see changes, which is why as soap bubbles move or the film on the gasoline film on the water moves or we walk past it, we see the colors change because we're actually seeing different wavelengths being interfered with as our angle to the film changes. And here we can see the iridescence on this large soap bubble this gentleman's making. And notice that we're talking about subtractive color mixing. So the colors that we're going to see in the bubble or the iridescence are the subtractive primaries. We're going to see magentas, yellows, and cyans. So we know that both sound and light are waves. Sound is a longitudinal wave and light is a transverse wave. But how did we figure out that light was a transverse wave? And one easy way to figure out if something is a transverse wave is polarization. Most of our light sources emit light that's unpolarized. And what I mean by that is, as the electrons vibrate and to emit the light, they're vibrating in all directions. So the light is coming out vibrating in all different planes. But if we can have the light vibrating in a single plane, then we can call it polarized. And the way we can create polarized light is using filters. So we can use a filter to, say, block horizontal light. So if light is vibrating in a horizontal plane, we can have a filter to block that. And then the vertical will still come through. Or vice versa, we can have a filter that will block vertical light and then the horizontal will come through. Or we can have a filter that will block the diagonal light and then the horizontal and vertical can come through. So we can block certain components and let the other components come through. And of course, it's going to let all the frequencies through. What we're just stopping is some of the light that's vibrating in a certain plane. This diagram here can help us understand how this works. So let's look over here on the left. And here we have light, and you can see the non-polarized light vibrates in all directions, vertical, horizontal, diagonal, etc. And let's say we have two vertical polarizers. And as the light hits the first vertical polarizer, it's going to block all other components, the diagonal and the horizontal, except for the vertical. And then if we have a second vertical polarizer, well, that light can come through that one as well. So it's just like if you stood over here on one side of a picket fence and your neighbor was over here on the other side of the picket fence, you could shake the jump rope up and down. Your side to side would not come through the fences, but your up and down would come through both fences. But let's say over here, again, we have the light coming out in all directions. We have a vertical polarizer, so that gets rid of all the light except for the light that's vibrating in the vertical plane. But now let's say we have a horizontal one. And again, the vertical can't get through there, and we already stopped everybody else. So now no light's going to get through. And it's just like if you're shaking the jump rope here, it comes through your picket fence, but now your neighbor has a horizontal picket fence, and of course that wave can't get through. So as they're holding the rope, they don't see any waves. And we see here in this picture how this works. So in this case, the light is being reflected off of the model's face and is coming through the two vertical filters to us. We can still see the light in the vertical plane that's coming off of her face through the two filters. And even though there's two of them, we can still see this area here. But now she turns this vertical filter horizontally. Now this is blocking horizontal light, this is blocking vertical light, and where the two overlap, no light comes through.